Good morning, class. So today we'll start on the part 2 of this course, and mainly for this part of the course, we will mostly review most of the concepts that we have learned in the first part of the course, but in different domains. Some of them could be repeated, like Laplace domains, which is this tutorial is about, but focusing on the concept of transfer functions. So therefore, while going through the second half of the course, right, you can also pay particular attention to the circuit analysis method that we have learned in part 1 of the course, because this serves as a review. Right? In particular, how to approach the problem is also very important. Even the circuits, right? How should we approach the problem in general? If you look at my solution carefully, usually I'll give a brief overview on how to approach the problem. And these are just suggestions, right? But there are many other methods which you can try. Okay, but in general, what I suggest is that before you start solving the problem, you should have something in mind, a rough plans on how you should approach the problems. Then you write down the details, right? So later on, you will see that most of it I will plan something, and then before we proceed to solve the problems. So this tutorial is basically about transfer functions, which we have discussed briefly in part 1 of the course. Right. Firstly, take note that transfer functions is basically a model, a circuit models, which give you the relationship between input and output. The concept of transfer function is general. It can be any input, any output of a linear systems, but for this course, we are focusing on circuit analysis. So therefore, what you will see is that maybe, for example, a voltage input, right, a source, and it produces a certain output, maybe the voltage across the resistors or voltage across the capacitors, right, voltage across inductors. And it can be current, right, input current, source, output voltage. It can be also output current, right? So inputs in general can be voltage or current. Output can also be voltage or current, right? Because we are focusing on circuit analysis. And we like to model the relationship between the inputs and output. What is the purpose of using transfer function? You use transfer function when basically you have a variations of your inputs, right? For example, one problems, right? You need to calculate the input for DC. Okay, another problems you need to calculate the input for the same circuits for AC. Okay, you may have other types of input. Okay, in this case, the methods that you have learned so far is that you just put the input there, then you do circuit analysis, find the output. Right? This is what we have done many times. Find the circuits variables in the circuits is actually to find an output that you are interested in the circuits. Okay, but rather than doing that over and over again for different input, what we do here is that we model a general model which gives you the relationship between input and output. And by doing so, right, you can put in any input and get your output. Okay, once you get the output, remember what we have done, expand it out by partial fractions, right? Take inverse Laplace transformations, that will give you the signals that you are interested. And you need not start from the beginning of the circuits, right? You just start from the model that you have obtained, multiply your model by your input, you get an output in Laplace domain. Then take inverse Laplace transformation by expanding them out as partial fraction, so as to get a linear combinations, right, of those variables that are available in the Laplace transformation table. Right, so today, basically, we will revisit most of the concepts that we have learned and put them together, right, in the concepts of we call transfer function. So firstly, take note that transfer functions give you the relationship between input and output. And the other thing to take note is that even if the question do not state these conditions, you can always assume that initial conditions are 0. Means that the capacitors, right, are not initially charged. Inductors, right, do not have initial magnetic energy, right? So the energy storage elements, in other words, do not have initial storage. Okay? They start from zero. This is what it means. Okay, in this case, right, remember that your circuit's components, inductors, will become just SL, right? Capacitor will become 1 over SC. If there are initial conditions, then there will be a model which will include some independent source, right, which represent the initial condition. So without initial condition, it's easy, just SL, right, 1 over SC. And as I said, you should remember this by heart, as if you remember Ohm's law, right? V is equal to IR for resistors, V is equal to I, SL for inductor, V is equal to I, 1 over SC for capacitor, right? You need to remember this by heart because you use it very frequently in the second part of the course, especially. Okay, even in frequency domain, right? Basically what we do is that we put S equal to J omega. Right? Then we go into frequency domain, which will be part of the second part of the course. And remember, right, for resistors, you have conductance. So similarly for impedance, right, which include resistors, inductors, and capacitors in this form, we will have admittance. Admittance is just 1 over impedance, right? 1 over impedance. So it's a name, as I said, it's defined to generalize, right, the concepts of inductance, SL, and the capacitor 1 over SC, right? We call impedance. So it's just inverted. SL become 1 over SL, 1 over SC become just SC. And when you use impedance when they are series combinations, and you use admittance when they are parallel combination, right? For series combination, add up the impedance. Parallel combination, you add up the admittance, and then you invert it to get back your impedance. Now, let us move on to question 1, tutorial 7. Find the transfer functions which give you the relationship between output over input. Right, so this is my input voltage, and this is my output voltage across the capacitor. Okay, actually, what you have learned last time was that you're given a specific input, say 5 volts, for example. Then you just perform circuit analysis to find the output across the components, right, a particular component. And we have covered that in the Laplace transformations circuits. So it's actually the same, except that here, right, do not put any particular input, put a general notation, VG, right, because we want to change it very frequently. Okay, we want to change it, for example, 5 volts. Later on, we may want to change it to an AC input, right? We may want to put an exponentially decaying input, or we may want to put some combinations of certain input, okay, which means that we need to find many outputs, correct? In this case, it makes sense to model a general relationship between input and output, so that given any input, right, given any input, so long as you can find the inputs in the Laplace transformation table or as linear combination of them, you will be able to calculate the output. So this is what we're going to do. And in transfer functions, as I said, always assume initial condition is 0, which means that you use SL for inductor, 1 over SC for capacitors. So this means that this is what we will do using zero initial conditions. Then inductor is simply SL, capacitor is 1 over SC. Once you transform your circuit into S domain, then the relationship between voltage and current will be a linear relationship like Ohm's law. Okay, which means that you can analyze the circuits as if they are resistor network, right? But of course, it's in Laplace domain. So after solving what you want, you still need to take inverse Laplace transformation, right? So this is the idea. Okay, you can sometimes just imagine, right? If all this that I circle are resistor, what will you do, right? What will you do to solve the circuits? Then you can solve it similarly. So as I said, there are many ways to solve the circuits, right? In fact, during learning stage, you should try a lot of them, so that maybe that will help you understand, right, which would be the simpler method. Okay, do not try to remember as steps, because once you remember as steps, right, given a slightly different circuits, not necessarily more complex, it can be simpler, then you may not be able to solve it, right, because you treat it as a fixed circuit, but circuits has different design. Okay, and you need to know the general methods, right, to solve them. So plan it, right? Plan it how you want to approach this problem. Okay, there are actually many methods, as you can see. Okay, in one method is that, for example, right, I'll just go through some. One method is that you can actually simplify this whole thing, right, into one equivalent impedance. Because if these two are resistors, you add them, correct? R1 plus R2. Okay, here is just Z1 plus Z2. Then it will be in parallel with this, correct? So you can simplify into one component, okay, which means that your circuit will look something like that. SL plus 1 equivalent impedance. Right? All this put into one. Okay, then you can see that by this, I can use voltage division law to find this voltage, VR. Right? VR is the voltage across here, which is also the voltage across the whole thing, because they are parallel. Now, after you find VR by voltage division law, then you can use another voltage division law, because this voltage VR, right, is divided by these two components, okay, according to the ratio of the impedance, right? So you should have something like that in mind. Okay, as I said, the method is not fixed, right? The method is not fixed, so you can use any methods. Here I use a slightly different methods, right, just to review some of the very important methods in circuit analysis, nodal analysis. Now, how do I do nodal analysis? Instead of using voltage divisions to simplify this, I don't simplify the circuits, right? I don't simplify the circuits because sometimes you can't simplify the circuits. Okay, why? Because if there are some kind of dependent source somewhere, correct? If your dependent source is needed in the circuit analysis, right, do not try to simplify, because once you simplify, you may mix up the variables. Okay, then this will cause some problem. So nodal analysis, mesh analysis allow you to analyze the circuit without having to go and simplify the circuits. Now this is what we do, we leave it, right? We leave it. We don't want to simplify anything. We define a node voltage, right? Remember 3 steps of nodal analysis. Assign node voltage, take KCL, right? Write down the equation in terms of the unknown node voltage, solve the equation. Here there's only one unknown. So this is what I'm going to drop out. I'll find VR, right, using nodal analysis. The only difference is that now you have a general notation here. So you find VR in terms of VG, right? Previously, actually, you have something here like 5 volts. Transform into Laplace domain, become 5 over S, then you just solve, right? Without realizing that actually it's also in terms of VG, right? It's just that VG is a particular value previously. Now we leave it. Why? Because you want to substitute lots of values inside later on, right? So as to get your output. Okay? So this is what we're going to do. Now, once you find VG, then you can use voltage division law to find V0, because this is actually your VR, right? VR is divided across 2R and VO. VO is the output that we're interested, according to the ratio of the impedance, right? Ratio of the impedance. So this is voltage division law. Okay, that means that my plan is to find the node voltages, right? Node voltage first in terms of my input voltage using any methods, right? Just now I show you voltage division law also can, right? And this is nodal analysis. Okay, you may want to practice mesh analysis, right? Also can. It's just that later on you need to relate back to your voltage. Okay, and this first step, actually any methods. Then after that, right, we use just voltage division law simply to find the relationship between V0 and VR. So I'm actually defining an intermediate variables so as to relate, right, my input to output. So this is what I'm doing here over here. Okay, the rest are the details which you need to solve them carefully. Okay, as I said, the concepts in week 1 and week 2 are extremely important because you use it until week 13 and as well as your senior years, right? So firstly, how do we find this node voltage? You have to understand first that node voltage means what? Okay, the voltage at this node, if this is 0 volts, right? If this 0 volts, this VR, then it actually means that the voltage across this resistor is VR, right? Because VR minus 0, right? VR minus 0 is the voltage across this resistor. So we are trying to find the voltage across these resistors by using nodal analysis. And nodal analysis says that if this is not known, call it a variable VRL, then write down an equations in terms of VRL and then solve the equations, right? How do we write down the equations? By KCL. So if you use KCL at node RL, you have inflow equal to outflow, for example. Now, this is assumed, right? We do not know really the directions, but logically, right, current should flow out from the positive terminal. Logically, even if it's not, then you get a negative answer, that's all, right? But for this one, we just write down equations. So assuming that you come out from here, come to this junction, split, right? Because this is ground, so most likely you flow to the ground. Right? Even if it's not, you just give you a negative, right, value, that's all. It's okay. That means your node voltage, if you solve it, it may end up to be a negative value. But for this case, we really do not know because it depends on our VG over here. So just leave it, right? Leave it in terms of VG. If you take Kirchhoff current law, right, starting from this branch, then we know that this is 0 volts. This is VG. This means that this node voltage is known. This VG. Okay, you are at 0 volts, increased by VG. So we are at this, right? Sometimes you can just visualize this way. You are at ground floor. You climb up, right, by a certain story, then you reach this floor. This floor is called VG, right? This node voltage at this node is at this potential. And potential difference is the difference between this VG and the ground, right? That is this VG over here and VR over here. Now VG is this node voltage, VR is on the other side. So the potential difference is VG minus VR. Ohm's law, right, says that divided by resistor is equal to current, but here is impedance, SL. So just divide by impedance. Okay, you can see that everything is the same, except that we use this concept we call impedance, okay, which is very useful in the circuit analysis because it enables us to convert the circuit as if they are resistor network and then solve it. The only difference is that in the end you need to take inverse Laplace transformation, right? Now this is the inflow, so we got inflow equal to outflow, okay, which is VR minus 0, right, divided by RL is the current flowing through the resistor RL. Now the current flowing through here is a series combinations of two impedance, is 2 RL, right, series you add 1 over SC, like something like Z1 plus Z2. Z1 plus Z2, right? And the voltage across this whole thing, which is this, okay, is VR because this is in parallel with this, right? They have the same voltage. Parallel means same voltage. VR divided by 2R plus 1 over SC is the current flowing through 2R. Also is the current flowing through 1 over SC because they are in series. So that means that we got inflow equal to outflow. Now normally what you have is that you have this as a specific value, then you solve for VR, correct? You solve for VR. Here we leave VG as a general input so that later on we can substitute any input into it. This means that we can proceed to solve it by separating VG, right, with VR. So I'll move VR to the other side of the equation. So all on the right hand sides are now VR. Okay, then the rest is to simplify it carefully. Now do not just read, right? Go and practice it until, as I always stress, if you cannot solve the tutorial problem without referring to the solutions, it means that there could be a missing concept which you need to put in more effort. Right? There's no point solving more and more problems if you can't do that, because it will not be very helpful. Right? If you can solve all the tutorial problems without looking at the solutions, right, I would say that then you can understand the concept well. Then there will not be any problems. Right? As you can see, actually tutorial problems are more complex. Okay? This is to enable you to understand the circuit problem better. Okay, over here, let us proceed to simplify these relationships. Right? So for what I did so far is that I just write down the equation using KCL, and then I group VR together, okay, and VG put on the other side. Okay, I'll reproduce this equation here, right, and then we'll proceed to analyze it. Firstly, I'll just combine this whole thing into this. Right? You can start by simplifying two terms at a time. For example, these terms, right? What you do is that you just do this R SL, right, divided by SL plus R, right? You get this combinations. Right? In fact, you see that SL divided by RSL give you 1 over R. R divided by RSL give you 1 over SL, right? So this is to combine. Then you do it similarly on this. Okay, this and this. You do it similarly, you get this one. Okay, this terms times this one, denominator. And then this term times this, give you this. And this term times this, give you this. In fact, you can see over here that this first term, right, divided by this term, actually cancel out this. Then you get back this term, right? Then the second term, so I look at it carefully. This divided by this, give you this one, okay, which is this one over here. So it's actually to combine everything together, right, so as to further simplify them. Now, next, notice that next notice that this term and these terms are the same, so I can cancel them out, right? Further simplify it, and therefore I get the relationship between VG and VR, right? VG and VR. But what I want is the reverse. I want to get VR in terms of VG. Remember, we are in the process of finding the transfer functions, output over input, but we define intermediate variables to get the node voltage in terms of the input, right? In terms of the input. Then we relate the output to the node voltage. Since the node voltage is related to the input, then you can relate the output to your input. So this is what we are doing. Okay, we have found this, right? Node voltage. So let us review the overall methods. As I said, you should have an overall methodology in mind. I'm finding this node voltage in terms of my VG. So I found it. Using any method here, I use nodal analysis, right, to review it. But actually, there's a simpler method using voltage division law, as I mentioned to you at the beginning, and you should try that. Right? Okay, then, after you found this, okay, relate this to the output voltage. Okay, and it can be done using voltage division law, because VR is this voltage, the voltage across the resistor. Okay, and then VO is the voltage across the capacitor, right? So voltage division law says that if you call this Z1, this Z2, voltage division law says that V0 is Z2 divided by Z1 plus Z2 multiplied by VR. Right? So Z2 is 1 over SC, Z1 is 2RO. So therefore you get the next equation. Okay, if you cannot remember voltage division law, never mind. Just use Ohm's law. What is the current flowing through here? Current flowing through here is the voltage across it, VR, divided by 2R plus 1 over SC. Right? So this is the current flowing through the 2R resistors, flowing through the capacitor. Now what is the voltage of the capacitor? The current flowing through it times 1 over SC, right? Ohm's law, IZ. So current flowing through it is this times 1 over SC is the voltage across it. Okay, which means that you should leave the method, right, flexible, and then be familiar with all the tools, right, so that you will be able to solve it. So finally, I invert this relationship to express V0 in terms of VR. Okay, this is obtained by multiplying the numerator and denominator by SC. So as to get rid of the fractions. Any questions so far? Okay, I'll reproduce these two equations here. And now you can see the meanings of doing all this. Right? First, I find VR in terms of VG. Right? In terms of VG. Then I relate my output in terms of VR. Okay, after that, you can see that what you need to do is to just put this into here. Then your output, right? Output will be related to your VR, and your VR is related to your input, which means that you get the relationship between output over input through, right, the intermediate variable, through the intermediate variables, and then you'll get the model we call transfer functions. So finally is to do this, right? Put this into here, you get output in terms of input. Okay, further simplify if you can, because for example this one cancel out, right? It makes sense to simplify it, and then we get the output over input, which is what we call the transfer function. Okay, as I said, this transfer functions, right, means that given any input, for example, just now we were talking about pi volts in Laplace domain is pi over S. Okay, you just substitute here. Then we will get our output as this. Right, put all the parameters of your RLC inside, expand it out using partial fractions, take inverse Laplace transformation, you can get the voltage, right, for any input. So here, this input, I can put any types of input, exponential terms. Okay, any other inputs, I'll only start from here, meaning that multiply input by your transfer functions, take inverse Laplace transformations after expanding out using partial fraction. So to review again, right, transfer functions give us the relationship between input and output. The purpose is that we have all kinds of inputs, right, that we need to put into the circuits to find out what is the output. Instead of solving the circuits over and over again, repeatedly for different types of input, we first model the relationship between and general inputs and output. After that, we will just use that model to find the output with any input, and then expand out using partial fractions, take inverse Laplace transformations, we'll get the output that we're interested. So this is the basic idea. And in transfer functions, right, always, right, this is always, even if it's not stated, you can just say that initial conditions are 0. Means that the energy storage elements are initially without any initial energy, right? No storage. They start from 0. Now, the previous question is actually a review, right, of what we have learned previously. In fact, we have talked about transfer function previously. And today's tutorials, right, basically is about one new thing. It's called stability, okay, which is what we have assumed, right, in the previous analysis. We always assume that the circuit is stable. Okay, but some circuits could be unstable, right? Unstable. So today we'll learn how to check the stability of the circuits, right? Before we proceed to find the output. So let us look at these definitions. Okay, when the circuit is stable, it means that the natural response is 0, right? It's 0. So as such, the steady state output of your circuits, this is your output. Okay, for a DC inputs, right here referring to DC, okay, that means step input, then will be a constant. Okay, actually this is quite easy to understand. If you have a DC input to your model, right, let's go back this one. If you have DC input to your model, it just means that finally, right, your output will be DC, correct? If you have DC input, finally your output will be DC, a steady state. So this is what it means. At steady state, I should have a constant. Constant means DC. Okay, constant means DC. Now, let us look at this again. DC inputs, it is called step input because you introduce a step change, right? 0, step up to, for example, 5 volts. Okay, actually, the output is called step response. Step response means that you have a step input. How your circuit respond to this step input, right? It's called the step response. So it's actually the output. Okay? It's the output of the circuits with a DC input, right? It's called step response. So remember that. Okay, we have seen this last time. I show you these animations of mass spring damper systems. Okay, imagine that you have this mass hanging on the spring. If you pull it to an equivalent positions, this is your initial positions, right? It means that you make the spring store with spring energy, right? So it has storage, store energy. Once you release the spring, because it has storage energy, you will move, correct? You will move, but how it moves is very complex. There are 3 types of response we have learned: under damped, critically damped, and over damped. Now, firstly, if there's no frictions, which means that if you do this experiment in the space, because there's no friction, once you release this, okay, actually the spring will just keep bouncing up and down, right? It's hard to imagine in Earth because we have air frictions. It will eventually stop, but in space, actually, there's no frictions, vacuum. So this thing will just go on and on, or at least it will last for a very, very, very long time, right? Before it finally decay. So without friction, it will just keep oscillating. But with friction, with air friction, for example, it has to come to a stop. Okay? Eventually, come to a stop. Equivalent positions. And how fast it stops will depend on how much damping you have. Correct? If you have more frictions, then more damping, then oscillations will stop faster. Now, if you put this experiment in the water, correct, you will never have oscillations. Then you have something that we show on the other side. Right? You will just move to the equivalent positions and stop there because the friction is too high in water. Okay, and that is usually the case of overdamp, right? It will move very slow. If you try to move in the swimming pool, you will never overshoot, right? If you do ice skating, tendency of overshooting is very, very high. Now, critically damped is the boundary where your overshoot just disappears. That means that you keep increasing your frictions until a stage where your oscillation just disappear. It's called critically damped. After which we call overdamped, right? Critically damped, right, is actually a certain boundary where your overshoot oscillation just disappear. Right? The moment when it just disappear is called critically damped. After that, it will be slower and slower. is called overdamped. Now notice over here that this means that your natural response all goes to 0. It means that when you release a spring, you will eventually come to a stop, right? You will not keep moving forever because there's no, in air, in earth, there's air frictions, right? So you'll just come to an equivalent position. So this is stable, right? This is called stable, meaning that you'll just come to a stop eventually. Now, actually, if you go back to look at your step response, RLC, para-RLC circuits, you'll see that your solution consists of two parts, right? The steady state values and the transients or the natural response. Now, these are three natural response, right? Depending on over them, critically under them. But you look at them carefully, they all goes to 0 when t goes to infinity. Right? All of them disappear. This all goes to 0 when t goes to infinity, means steady state. Now eventually then you come to a steady state value, right? VSS, which is a constant, okay? Because this DC means it's constant. So in other words, this, right, if you go back to read this again, it's become clear. The circuit is stable if the natural response all decay to 0, right? Natural response all decay to 0, and you're only left with a steady state response, which is this one, right? So the limits of this go to steady state values. Okay, for DC, steady state value is a constant. So this is what it means. Okay, that means that we have gone through stable circuit without realizing, right, that it's stable. So today the only thing new is that what is unstable, right? That means what is the other way around. Okay, I'll go to question 7.5, right, to let you understand what is an unstable circuit. Now firstly, this problem says that step response of a linear circuit. What is step response? Step response is the output of the circuits in response to a DC input, right? In response to a DC input, because DC is the step input. Now, output in response to a DC input is the step response, and this is given 2e to the power 100t. The ut is just being divided by 1 for t, multiplied by 1 for t greater than 0, right? So you don't have to worry about this. It just means that this is equal to this for t greater than 0. And okay, next is to note that this output goes to infinity as t goes to infinity. It doesn't go to 0, right? It doesn't go to 0. It doesn't go to any constant value. Okay, actually, if the system is stable, if you have the DC input, it should give you DC output. Okay, if not, right, then there's some problems there. Either is it unstable or it could be oscillation. Okay? So here, if the circuit is not stable, right, there's no steady state. Okay? No steady state meaning that you will just keep increasing. Your output do not settle down at DC. Okay? You will just keep moving and moving to infinity. Okay, of course, in practical system, practical circuits, you will never reach infinity, but it means that you will lead to very high output. For example, your current could be too high that you burn the circuits, right? Voltage too high, okay, which will means that this should be avoided. Okay, of course, one way to test whether is it stable or not is to pump in input and then check whether your output goes to infinity or not. But you know that, right? This is not the right thing to do because it's dangerous. It means that you'll burn something, right? Trip the circuit breakers or lead to some serious problems, right? Fire hazards, etc. So as engineer, we need to first ensure that this will not happen. DC input give you DC output. Stable, finite. Unstable means DC input give you infinite output, right? So if your output goes to infinity at steady state, then we say that it is not stable, unstable. Okay, and you have seen the three types of response. All right, three types of response. This is under them, right? Them, right? Critical and over them are quite similar. Quite similar. It just means that how slow are they, all right? So I just put two of them. Now stable means put in a DC input. Eventually it will settle down at DC output, right? Steady state will be a DC output. So this is called stable. Unstable means that you put in a DC input, it will not settle down at a DC output. Okay, one of these we have seen, it just keep growing to infinity, but this oscillation can also grow to infinity. Okay, this is what you look like. Right, you just keep increasing towards infinity. So at this or not from the transfer functions, right? The transfer functions give you the relationship between input and output. So it should tell you something about your output, right? Whether it goes to infinity or not. So this is a concept. Okay, we can actually check whether the circuit is stable or not by the transfer functions. Even before we implement it, we already know whether is it stable or not. And this is how we will do it based on the location of the poles, right? Based on the location of the poles. The location of the poles will tell you whether the system is stable or not. Our next question, what is poles, right? What are poles? Now, poles are actually obtained from the denominator of your transfer functions. Okay, you can see from so many examples that transfer functions are basically a ratio of two polynomials, right? Two polynomials means that you solve the circuit problems, you end up with polynomials in the fraction forms, which we call the transfer function. Now, in general, right, you can call this numerator and denominator. For example, this is your numerator, this is your denominator. And your numerator can be a polynomial. Okay, we will put a general one with m order. For example, in this case, m equal to 2, right? M equal to 2, the highest order. Okay, the denominator is also a polynomials. To differentiate them, we put a different order, right? N. So for example, n equal to 3. Okay, this means that your transfer function is just a ratio of a numerator divided by a denominator in Laplace domain, right? S is Laplace variable. And we know that this polynomial can be factorized, right? Can be factorized. For example, in this case, if you take out s, then you have s squared plus 7s plus 10. And s squared plus 7s plus 10 can be factorized into s plus 2, s plus 5. Okay, but some you can't factorize into real factors. But however, you can factorize them into complex, right? Complex first order factors. Okay, in either case, it means that you can factorize, but some may be real, some may be complex, right? Okay, in general, polynomials can be factorized, right, into many first order factors. In fact, we have done this so many times, right? In inverse Laplace transformations, after you get the solutions, correct? You factorize them. Right? We don't factorize the numerators, just factorize the denominators, and then try to expand it out using partial fraction. So this is what we have done, actually, except that we also factorize the numerators, right? To define something we call zeros. Okay, 0 is the value of s which make your transfer functions equal to 0, as the name implies. So naturally, when the numerator is equal to 0, right, then your transfer function is equal to 0. So it's very easy to remember, right? 0, transfer function equal to 0, then numerator equal to 0. Numerator equal to 0 means what? S equal to negative z1 or negative z2 or negative zn, right? So these are the zeros, the locations of s which make your transfer function equal to 0. Now poles is actually the value of s which make your transfer functions goes to infinity. Right? One goes to 0, one goes to infinity. Now when does it happen? When your denominator is equal to 0. Right? When your denominator is equal to 0, then your transfer function will go to infinity. And this happens when s equal to negative p1, negative p2, or negative pn. Right? So these are called poles. These are called zeros. Now remember, we are in the process of checking whether transfer functions or circuit is stable or not. Right? To do that, we need to check the poles. And now we know that the poles are defined as the value of s, right, which make your transfer functions go to infinity. Right? And at the same time, we also introduce something we call 0. Now 0 does not play a major role in your stability. For this course, you can just ignore it. Right? Just ignore it. Just treat it as something which make your transfer function equal to 0. The important thing is your poles. Right? Important thing is your poles. Now let's move on to the poles. Poles are the value of s which make your transfer function go to infinity, which means that s is equal to 0, divide by 0, s equal to negative 2, right? Negative 2 plus 2, 0, divide by 0, s equal to negative 5, also divide by 0. If you divide by 0, then your transfer function goes to infinity. So these are poles. Okay, next questions. How does poles affect the stability of the circuits? Right? We are checking whether the output will go to infinite or not. And this is unstable. Okay, if I have a DC input, is you give me DC output. If not, it's unstable. So it can be checked from the poles of your transfer function. Okay, let's go through one example first. If I have these transfer functions, what are the poles? Negative 1, negative 2, right? Negative 1, negative 2. And suppose that you have an input, transfer function is output over input, multiplied by input give you output, right? For example, if your input is 1 over s, then put it into here, okay, you get this one. This multiplied by 1 over s, give you the output. So this is my output. To get the output, you expand it out using partial fractions. And then take inverse Laplace transformation. Okay, this 1 over s, it gives you a unit step input. It just means 1 for t greater than 0, right? For this one, you give it 2 to the power e negative t, right? Take note there's a negative sign, because if you check your Laplace transformation table, s plus a give you e to the power of negative a t. Okay, which means that if your poles are negative, right, then you have negative value here. All right. And what this means? This means what? Natural response goes to 0. Natural response will go to 0 When t goes to infinity, that means at steady state. Okay, notice that your natural response are relating to your transfer function. Okay, your forced response actually is depending on your input. If you put in 1 over s, then I have this term, right? This term, as pair of changing partial fraction, you have this term. You put in other input, then you have an output related to the different types of input. Okay, but your transfer functions, right? The natural response is relating to your transfer functions. It must goes to 0. Okay, otherwise is unstable. Now let me show you an unstable response. I just reverse the sign, right? Positive change to negative. Positive change to negative. So now I have poles which are positive. Okay, if you plot it up on the S-plane, it means that they are on the right half plane. Right? They are now on the right half plane. Previously, they were on the left half plane. Okay, you invert these signs, right? And then you expand it out by partial fraction. Obviously, this will be negative. If this is negative, then this will become positive. Because negative become positive. And look at this, it goes to infinity now. Okay, which means that it becomes unstable. So the locations of the poles, right, will determine the stability of the system, because you make your output in time domain goes to infinity, right? That's the definitions of unstable, go to infinity at steady state. Okay, we have seen that if both of them are on the left half plane, it's stable. If both of them are on the right half plane, it is unstable. Now let me ask you a question. How about one left half plane, one right half plane? Is it stable or unstable? For example, if this is -1, this is +2, is it stable or unstable? Now just look at time domain, right? Even though one goes to 0, the other one still goes to infinity. So therefore the output still goes to infinity. Okay, this means that in order to ensure stability, all the poles must be on the left half plane, right? All of them must be on the left half plane. If any one, just one on the right half plane, it means unstable, right? Because that will lead to some exponentially increasing term in your time domain. So if you go and review your notes again, all this I actually extract out from your notes. Okay, except that I just invert some of this, right, to show you what happened if it's the other way around. If you go back to review your notes again, right, this is what it means. Okay, after you get your output, you expand it out using partial fractions, right? You'll get a lot of this first order factor. So if this is positive, okay, that means that S is equal to -P is your poles, right? Then you'll be on the left half plane, it means that you will decay to 0. Okay, meaning that it is stable, right? But on the other hand, it is positive. If your poles is positive, your output will be infinity, right? Because you just invert this become positive, because this is negative, then you goes to infinity, means this is unstable. And similarly, you can review, right, some of this concept, marginally stable. Okay, because we know that on the left half plane is stable, right half plane is unstable, but how about in between? In between is called marginally stable, right? Easy to understand. Left unstable, left stable, right unstable. So this boundary is called marginally, right? Marginally stable. Okay, marginally stable is, you can see that, right? If you have this poles at the origin is 1 over S, then you have a unit step, right? Unit step, which is a constant. Okay, which is a constant. But if you increase it further to the right hand plane, then it will become unstable. Okay, so it's something like that. Left half plane, right, decay to 0. Okay, right half planes go to infinity. Okay, in between, right, is a constant. neither decreasing or increasing, right? Neither increasing or decreasing. And basically, right, we must ensure that all the poles are on the left half plane. Okay, otherwise it will be unstable. Okay, and sometimes, right, too close to the imaginary axis, marginally stable, is also not good, because any slight uncertainty, right, will push it to the right half plane and make the circuits unstable. So usually we have some margin, right? We want to ensure that, right, not only is on the left half plane, it should have a certain safety margin, right, from the boundary of instability. And you can also review the imaginary case. Okay, in some cases we cannot separate them into real fractals, but they can be factorized into imaginary, right, imaginary poles, and basically then this will lead to oscillations, right? So this is actually in the part 1 we call case 3. Okay, case 3 is the underdamped response. Underdamped response, you know that your oscillations, but these oscillations will decay to 0, right, eventually. Okay, because over here you can see that same thing, right? This terms means that it's exponentially decaying to 0. It actually means that you have a sine wave with a magnitude which is decaying to 0, right? This is equal to 1 for t greater than 0. You have a sine wave which decay to 0 as t goes to infinity. And notice that this phi, right, depends on this real part of your imaginary poles, right? Only the real part play a role in your magnitude. Okay, the other one is just the oscillating frequency. It does not play a role in stability. So let's look at the real part, whether is it on the left half plane or right half plane. Right? Similarly, if the real part is on the right half plane, then you've got positive value, which means that you will grow, right? Magnitude will grow to infinity. So in general, we check whether the poles, right, is on the left half plane or on the right half planes. Okay, and if there's no poles on the right half plane, okay, which include the imaginary axis, right, because that is quite risky, then we say that it is stable. Otherwise, it is called unstable. Any questions? So this slide summarizes everything. Get the transfer function, check the poles. If the poles on the left half plane is stable, right? If it's on the imaginary axis as well as on the right half plane, we call unstable. Okay, let us move back to 7.2. 7.2, you're given circuits, right? Given the circuits, now you have a dependent source, correct? You have dependent source. Therefore, unlike the first problem, you can't really simplify these circuits by series parallel combination anymore. So therefore, right, you need to learn a lot of methods, including nodal analysis, mesh analysis, right? Because in some cases you can't simplify them. And also take note that, right, for circuits with dependent source, right, it is not advisable to simplify those involving the variable. Right? For example, here you have Vx, which then is defined for this. For example, if you use source transformations, right, then you basically change your Vx to another variable somewhere in the circuit, because source transformations only says that the terminal properties are equivalent, right? It does not say that your variable after transform will still remain the same. So I'll say that if you have, right, dependent source, do not touch those, right, components involving your dependent source, right? This Vx, do not change it. Once you change it, you completely change your circuits. So this means that you should analyze the circuit as it is, right? Using methods such as mesh analysis, nodal analysis. Okay, here actually is the same, similar to one of the questions, except that here we have a current source. Here we have a dependent voltage source, this voltage, right? This voltage is dependent on this voltage across the 4 ohm resistor. And we need to analyze the stability of the systems with values of different mu. And take note that mu greater than 0 is given, right? It's imposed by the question. Now, as I said, once you deal with transfer functions, always assume 0 initial conditions, which means that inductor convert to SL, capacitor convert to 1 over SC. Okay. This basically means that my capacitor, okay, will be this 1 over SC. C is equal to 0.1, so 1 over 0.1 is 10, right? And L is equal to 2, so you get 2S. Okay, put everything into Laplace domain. All the variables are in Laplace domain now. Then treat this as circuits as if it's resistor network, and then try to analyze it. Okay, as I said, once you see dependent source, do not try to use any source transformations, because if you do that, then you change this circuit, which means you change the definitions of this variable. Right? You change the definitions of this variable, so just leave it. Okay, which means that you can't do anything except that you must use nodal or mesh analysis. Okay, either one is fine. The whole idea is that I define an intermediate variable. Now, same thing. I try to relate my intermediate variable to my IG. Okay, then I try to relate my output current to my intermediate variable. Then I will link up my output to my input. So this is the idea. Find Vn in terms of Ig. Then find I/O in terms of Vn. So this is the idea. Okay, here I use nodal analysis again, because it's easier for me. But if you want to use mesh analysis, it's also fine. If you use mesh analysis, then you only need to define around this loop, which is your I/O. Right, but here you have IG. Right, you have IG, so this branch will be IG minus IO, correct? IG minus IO. Okay, if you take Kirchhoff voltage law around this loop, you can also get the relationship between output over input. Right, so this is also fine. You should go back and practice it. Now, same thing, right? This loop is known, IG. Mesh current is known, so do not need to take KVL at this. Just take KVL at this mesh, because I0 is what you want to find, right? You should go and practice that. But here I'll do nodal analysis again. Okay, I define node voltage. Okay, define node voltage. Then I take Kirchhoff current law. Inflow equal to outflow. Right, inflow equal to outflow. IN, IO. I want to relate IO to IG, right? This is an intermediate. Now, inflow is IG. This current is known, right? And outflow, Vn divided by series combination, 2s plus 4. Series, Vn divided by equivalent impedance, 2s plus 4, give you the current flow through, right? The impedance to 0 volts. Okay, next over here. Here there's a voltage source, so this means what? This 0 volt, you climb up, right, by mu Vx. So this node voltage is mu Vx. Okay, you are at 0 potential, you climb up by this potential difference, positive, climb up, right, then you reach mu Vx. Okay, so this means that this is respect to ground, right, respect to ground. And the potential difference is therefore Vn minus mu Vx, right? Impedance series 10 over S plus 8. This is your current flowing through this impedance, right? So inflow equal to outflow. Okay, after that, notice that there's still this Vx, right? Remember, your nodal analysis is to find this node voltage. anything that is not expressed in terms of node voltage, try to relate it to your node voltage. Right? Then you look at Vx. Vx is defined here. Vx is the voltage across the 4 ohm resistor, right? Which means that you can use voltage division law to get Vx, right? Because this is Vn. Vn is divided by Z1 and Z2, right? So Z2 divided by Z1 plus Z2 multiplied by Vn is your voltage. Okay, the other way to look at it is just Ohm's law. Okay, as I mentioned several times, you can also use Ohm's law. What is the voltage across these two? Vn. And what is the current flowing through this branch? Vn divided by 2s plus 4, right? So this is In. Ohm's law, In times 4 give you the voltage across 4 ohm resistor, right? Then you relate your Vx to Vn. Okay. After that, go back into here, you only have Vn or Vn. Okay, which means that I have relate my Ig to Vn. Okay, after that, invert it. What invert it? It means that express Vn in terms of Ig, right? Vn in terms of Ig, so we will take out Vn, okay, and take out some of the common factors, right? This means that this will introduce this additional terms over here, okay, and after that, okay, we will invert this relationship. Okay, I'll just reproduce these terms over here. Okay, and then invert this relationship. Okay, what we want is Vn in terms of Ig, right? Rather than Ig in terms of Vn. So just invert it, and this is what we get. So we managed to relate the Ig, right, to Vn, right, after inverting this relationship. And lastly, right, I just group all the corresponding terms together, okay, and then normalize it if you can. For example, here, right, all the coefficients are even, right, which means that you can divide by 2 to further simplify it, and this will become, right, s squared, and group all the s term together. Okay, group all the constant term together, and s squared there's only 1. So this is the transfer functions, which give you the relationship between output, inputs, but this is output nodes, and this is the intermediate variables, Vn, to Ig, right? Not yet the transfer function. Transfer function is I0 over I in terms of Ig. Here we have obtained the relationship between the node voltage, the intermediate variables, in terms of Ig. Okay, next, let's go back to our overview. We find Vn in terms of the input, right? So this is what we have done so far. By using nodal analysis, mesh analysis is also fine. Okay, just take KVL around this loop, noting that this, right, this current, right, be careful, this current is Ig minus IO, Ig minus IO. So in fact, you do this, you can also get the same thing, right? Go back and try. Okay. And our Vx, right, you have to express in terms of Ig minus IO also, right? It can be expressed for Ig minus IO times 4, right? So this Ig minus IO times 4 is your Vx. So everything can be expressed in terms of input output. Then you can also get this. You should go back and try, because do not fix your methods, right? Give you more choices so that you can use different methods for different circuits. Now, in general, as you can see from the two problems, right? The first one, because there's no dependent source, so I can use a lot of methods. I don't I can simplify my resistors, use voltage division law, but for this case, they are dependent source, right? So the methods become narrow. Right? Try not to change the circuits, which means that nodal analysis, mesh analysis are a good choice, right? Without further simplifying anything. Okay, well, I have obtained this. Next, I need to relate my output current to my node voltage. Right, this is quite easy because using Kirchhoff current law, inflow equal to outflow. Right, it's outflow. This is my inflow, and this current is the current flowing through this branch, which is just Vn divided by 2s plus 4. Right, Ohm's law. Vn divided by 2s plus 4. That means the outflow is inflow minus this one. Right, my inflow, some go to here, some go to here. Okay, which means that I relate my output to my Vn. Now this is okay, this is Ig, right? Output in terms of input, okay? And in terms of Vn, and Vn can be expressed in terms of Ig. So what you need to do is put this into here, then everything will be in terms of Ig. Then I get the relationship between output and input. Okay, once you get to this step, is quite safe already. Right, the rest is actually to do it carefully, right? Do it carefully, step by step. Okay, by simplifying the transfer functions, combine these two, you get this, and this will be my transfer functions. It gives me the relationship between output in terms of input. So that given any input, right, I can calculate my output. Any input, I can calculate my output. Now, remember that we need to check the stability of the circuits, right? And how do you check the stability of the circuits? Check the poles. Where are the poles? The poles are where your denominator is equal to 0, right? Value of S, where your denominator is equal to 0. Now, in this case, there are some mu here, not some constant terms. But in this case, you still can find the value of S, which make it equal to 0. Okay, actually, right, this is something that you have learned before. You just need to relate to it. Suppose that you have a polynomial ax squared plus bx plus c is equal to 0. Right, then actually this one you can, everybody know how to solve it. Negative b plus minus b squared minus 4ac square root divided by 2a. Now why there's a plus minus? Because second order means two poles, two solutions, right? So one is called x1, the other one is called x2. x1 is equal to negative b plus, x2 is equal to negative b minus, for example. Then you have two of them. So if you know this, then this is also easy, right? This is called the characteristic equations. The solutions of the characteristic equations is called the poles, right? It's called the poles, which means that you have two solutions, S1, S2, negative b plus minus b squared minus 4ac, a is equal to 1, c is equal to 5, right? 4ac become 20 square root divided by 2a, 2 times 1. And this can be further simplified by taking out 2 square. Right? If you take out 2, it becomes 2 square, right? Because there's a square here. Then basically here will be 3 minus mu square, right? I'm taking out this term. Taking out the 2 from this term, so I get 2 square because there's a square here. And then this term over here, similarly, I can take out 2 square because this is 4. 4 times 5, right, is 20. Okay, you take square root of this, it means what? It's equal to 2 square root, right? 3 minus mu square minus 5. Okay, then 2 divided by 2. Right, 2 divided by 2. And here simplify. You give you this and this. Now remember, these are the poles. These are the 2 poles, right? Second order. There are 2 of them. One is plus, one is minus. And this poles must be on the left half plane, right? Must be on the left half plane in order to be stable. Okay, in order to be on the left half plane, okay, we must ensure that mu is less than 3. And mu greater than 0 is given by the question, imposed by the questions. So mu must be less than 3. Now, if not, right, it will be unstable. Okay, let's go through it for a condition where it is not satisfied. Mu is equal to 4. Right, now mu equal to 3 means this term goes to 0. Right? This term goes to 0. And this term will become negative 5, which means that you're on the imaginary axis. Okay, I say again, you put mu equal to 3. Mu equal to 3, then you are on the imaginary axis. Because why? Here, this is 0, then you have square root of negative 5. Square root of negative 5 is actually j square root of 5. Right? And the other one is negative j square root of 5. So you are on the imaginary axis. Remember, stability must exclude imaginary axis and right hand side, right half plane. So therefore, j equal to 3 excluded. Right? This is less than, strictly less than. How about 4? Right? You check 4. You put 4 here. Then you get actually positive 1. Right? 3 minus 4 is negative 1. Negative, negative become positive. And then here is still imaginary. 1 minus 5. Right? 3 minus 4 is 1. 3 minus 4 is negative 1. Negative 1 square is 1. 1 minus 5 is negative 4. Okay, which means that this is equal to J2. So it is on the right half plane. Right? Because this 1 negative J4, right? Or on the right half plane. So therefore, if mu is greater than or equal to 3, this is unstable. We want it to be stable, so it must be less than 3, right? So let's look at mu equal to 3 again. Okay, it's required by the questions. If mu is equal to 3, then you just put mu equal to 3 here. You get 2 minus 6 is negative 4. So the 0 are at 4, and there's one more here, right? Equal to 0. So zeros are where the locations, right, of the s, which make your transfer function equal to 0. Poles are where s squared plus 5 is equal to 0. So you either solve this s squared plus 5 equal to 0, give you this one, or you go to this if you have the solution, right? Mu is equal to 3, then you get 0. Mu equal to 3, you get square root negative 5, which means what? Plus minus j square root 5. Okay. Then mu is equal to 2. If mu is equal to 2, okay, then I'll just go straight to the poles. If mu equal to 2, put 2 here. 3 minus 2, negative 1. 3 minus 2, 1. Right? 1 minus 4. 1 minus 5, negative 4. Negative square root of negative 4, j2. Right? Because j is square root of negative 1. Basic definitions of j. So it's imaginary, right? But on the left half plane, because your real part is negative. Okay, if your real part is negative, it will be on the right half plane. Because this negative 1 plus j2 or minus j2 is still on the left half plane. Or mu equal to 3, then it starts to enter the unstable regions. If mu is greater than 3, then right, it will be on the right half plane. Okay, you can try as what I did, mu equal to 4, for examples, and you see that you will become positive 1, right? Increasing mu further will increase your real part as positive value even further. So in other words, we can derive the transfer functions, check the location of the poles, which is the denominator, right, of the transfer function equal to 0, and then use that to check whether our circuit is stable or not, okay, before we further analyze it. Now, if your circuit is unstable, that means if there's a pole on the right half plane, then you need not find the output anymore. Just say that the output is infinite, right? Output is infinite. If it's stable, then you proceed to find the output. So the whole thing goes this way. It derive the transfer function, check the poles. If the poles are on the left half plane, proceed to find the output y. If the poles are on the right half plane, just look like just do something like question 5, say go to infinity. Right, goes to infinity, there's no steady state values. Okay, let's look at another circuits. Now, unit impulse response means that you put in an impulse, right? Unit step response means you put in a step input and you want to see how your output responds to these two inputs. How your output responds to these inputs. Okay, here we have two inputs, so it makes sense to derive transfer functions. Right? In fact, unit pulse is relating to your transfer function. Okay, let's look at this circuits again, and we have energy storage elements. So once you see energy storage elements, method not specified, use Laplace transform, right? No need to think, use Laplace transform because it's easier to do that in S domain. Now, Laplace transformation says that convert C to 1 over SC. S is 20 times 10 to the power of negative 9. 1 over 20 times 10 to the power of negative 9 is 50 times 10 to the power of 6, right? 1 over C. So this is 1 over C, and they give us this value over here. Okay, over here, I'll use a more general notations here, okay, but actually it just means that my Z in is 10K, which is 1 times 10 to the power of 4, okay, and my ZF, right, my ZF is actually these two parallel combinations. Okay, this is something like your Z1, Z2, right? How do you combine this? Z1, Z2 divided by Z1 plus Z2, correct? Parallel combination, Z1, Z2 divided by Z1 plus Z2. The only thing is that you have S term, so leave it in S domain, right? Leave it in S domain, try to simplify some common terms, and this is what we get. And so far what we have done is that we have just simplified this into this simplified form, right? By parallel combination. Or you can add up the admittance and invert it, right? It's also fine. Okay, as I mentioned before, right, op-amps, only two properties that you need to remember. Okay, one is that this V voltage at the positive terminal is equal to the voltage at the negative terminal, right? Because of the infinite gain. Because of the infinite gain. Secondly is that your current entering the negative terminal is equal to the current entering the positive terminal, and they are both equal to 0 because of the infinite resistance of the op-amp. Okay, this basically tells you that the current here is 0 and the node voltage here is also 0 because the positive terminal is connected to 0, ground. So if this is 0, then this is 0. If this is 0, because V plus equal to V minus, then it is telling you that this is 0 volts, right? This is 0 volts. Okay, that means that even if your op-amp basically is just telling you that some of the node voltages, right, are equal to some values or in terms of some variables. Okay, after that, then you can just treat it as if this op-amp is not there anymore by imposing the voltage and current condition, right, due to the op-amp property, and then analyze the circuits. Okay, for example, over here I'll use KCL inflow. This current inflow is VG minus 0 because this is 0 volts, voltage across it, divided by Zn, inflow, right? And then I have another inflow from output. This is a feedback voltage through this impedance. So V0 minus 0, which is V0, divided by Zf is another inflow coming in from the output, right? Because I'm assuming everything flows through the ground. Okay, next, equal to outflow. Outflow is 0 because of the op-amp property. The current cannot flow into the terminals, so outflow is equal to 0. Then I get this equation. Okay, from this equation, I already can get my transfer functions because everything is input and output only. I just move this to the other side of equations, right? Express V0 in terms of V in. Then I get my transfer function. And then remember what is your ZF? ZF is this value, right? And Z in is this value. So we just put this over here. Here we get ZF over Z in. Don't forget the negative sign, right? Because you bring this, you get a negative sign. Bring it to the right hand side, you get a negative sign. Okay, after that, to divide some of the common terms, 10 to the power of 4, left with 10 to the power of 2, which is 5,000. Then you get the transfer function. Now, remember, you need to check the poles, correct? This means what? S is equal to negative 500. Right hand side, stable. So we proceed to find the output. If this is on the right hand side, then just say that, right, or both output will be equal to infinity. Okay, but this is on the right, on the left half plane. So we can proceed to find the input. Okay, first one is called unit pulse, means that you pulse it. Right? Imagine that you can do that, and then you want to check what is your output. Okay, in fact, this is relating to your transfer functions only, right? Because your pulse means that it's equal to 1. Unit pulse in Laplace means it's equal to 1. So take inverse Laplace transformations of this, you can see that this goes to 0, right? So it's finite. Okay, for unit step response, it means that you put in a unit step input. You want to see how your circuit responds, how your output responds to this input, so it's called unit step response. Okay, this means that I have a finite input because it's constant of 1. Okay, then if I put this inputs into here, okay, where this is my transfer functions, right? I'll get my transfer functions multiplied by input, and this gives me my output. So everything starts from here. You can see any input just change. Multiply your transfer function by any input, then expand it out by partial fractions. I can get my output. Right? So the nice thing of transfer function is that I can change this. And you can see that these terms, right? Your force input, your input to the circuits will produce DC output. 10 over S is actually DC. Okay, this is relating to your natural response, your circuits, right? Your circuits. It means that it's not depending on your inputs. For force input, you produce force response, right? But your circuits is relating to your parameters of your RLC, and this is called your natural response. In Laplace domain, it's 1 over S plus 500. In time domain, it's e to the power of negative 500t. So this is stable. It goes to 0, your natural response goes to 0, and at steady state it settles down at -10, right? The natural response goes to 0, at steady state it goes to -10. So this means that you pump in a constant voltage of 1. It gives you a constant voltage of -10 at infinity, at steady state. So let me summarize everything by this slide. Okay, we found the outputs. If you want, you can separate them into two parts. And this is a forced response, meaning that it's forced by your input, right? You have an input, DC, you put it in. This is how your output will respond to your input at steady state. It's equal to -10 at steady state. Okay, but there's a natural response which will affect your transients. In fact, over here, if you put t equal to 0, then you get 10, right? 10 minus 10 is 0, which means that it starts from 0. Okay, and then it will tend to -10 as t goes to infinity. So this is how your response looks like, right? It starts from 0 and goes to -10 as t goes to infinity if you pump in 1 volt, right? If you pump in 1 volt, you start from 0. At steady state, it goes to -10. Now, -10 is referring to the steady state voltage, right? Before that, it's called the transient. It's called the transient. So therefore, there's a steady state gain also, okay, which is related to your AC analysis as well. AC analysis means you put in an AC input. At steady state, you produce the AC output, right? AC output. And then there's a steady state gain. Okay, for this one is DC. If 1 volt gives you -10, then the gain is -10, correct? This basically means that you put in 2 volt, you give you -20 volts at steady state. Okay, you can try. Put in a step response 2 over S, right, in Laplace domain. Then you can get -20 at steady state. Okay, for the last questions, I'll go through it quickly because this is just to get you ready for the AC analysis. Okay, for this simple circuits, output over input can be simply obtained by voltage division law. Right? And we have two inputs. One is AC, one is DC. So it makes sense to use transfer function, right? So that for any input, we just start from the transfer function, multiply transfer function by input, we get the output. So firstly, you have to convert your circuits into Laplace domain. 1 over SC, 1 over C give you this, right? You can either put the numerical values or put it in general, right? Up to you. And inductors, okay, will become SL. Will become SL. Now, since this right deal with some mini 10 to the power -3, I'll just put L first, right? Later on, then we simplify it. Okay, but you can also go direct to get the values, right? It's up to you. So here I'll put it in general, so just to show you something. These are series RLC, remember? Series RLC. And if you add up RLC impedance, you get something like this. Right? Ignore this part first. You get this something like this. R plus 1 over SC plus SL, correct? Series. Now, voltage division law says that this V0 is a portion of VG. V0 is a portion of VG according to the ratio of the impedance. Z1 divided by Z1 plus Z2 plus Z3, right? Z1 plus Z2 plus Z3. Or you use Ohm's law, current flowing through here is VG divided by total impedance, right? Multiplied by SL, Ohm's law, give you V0. So this gives me the transfer function directly, simply by voltage division law. Okay, then I can proceed to simplify it to this transfer function, right? So first I get rid of this by multiplying by CS. Okay, then I normalize it by dividing by LC. Okay, I'll get this. Now, this part, right, it should remind you something. Remember your characteristic equations of series RLC. Okay, this is your 2 alpha. This is your omega 0 square. Right? So by doing this, you can see that you can get the formula that you need. Okay, very easily. In series RLC, add them. I normalize it properly so that you get S squared plus 2 alpha plus omega 0 square. Then you know that alpha is R over 2L, omega 0 is square root 1 over LC, right? Then you can solve time domain problems by checking the value of alpha with respect to omega 0 and then write down the solution. Okay, here we use Laplace domain because if the method is not specified, right, natural choice Laplace. Okay, it is said use time domain analysis, you have to use time domain. But you can use Laplace to check your answer, right? But the method must be in time domain. Okay, so I substitute all the values of RLC into it. Okay, then I can get this value, right? So this also means that this is your 2 alpha. So alpha is 1000, and this is your omega 0 squared, right? So omega 0 is 2 times 10 to the power of 3. Okay, so actually we know what kind of response it is from this already. Okay, then I proceed to look at this denominator. Okay, actually what you should do is you should factorize it S1, S2 first. Then you know that it's on the right half, it's on the left half plane, right? So I'll skip this step. You can check it. It's on the left half plane, so it's stable. Okay, here what we are doing is that we'll briefly go through frequency domain analysis. And I'll go through it very quickly because we'll repeat it again in the subsequent tutorial after two-port networks. This is just to let you have a feel of it. Put S equal to J omega, you enter frequency domain. Right? Frequency domain, S equal to J omega. Okay, you put S equal to J omega. And what is omega? Omega is the frequency of your input for AC. S equal to J omega is for AC analysis. Frequency is relating to your source, omega equal to 2000 in this case, right? Given by the problem. So if you put omega equal to 2000 into all these values, okay, then you can get this transfer functions with this frequency, at this particular frequency. Okay, for AC input. Now next is to take note that J square is equal to -1. Always remember that because J is defined as square root of -1, right? So you square it, you get -1, which means that some of this term will become real. Okay, some of this term will become real. In fact, if you square this, you get negative value, and it happens to cancel out with this, right? These two, you square this, you have the same value but reverse sign, so they cancel out each other, and you only left with these two. Right, you only left with these two, so in the end you get a negative sign here. J squared is equal to -1. Okay, square this, you get the same value, cancel out, you get -1 divided by J, which is J. So this is your EE207, right? This is in standard form. Standard form means what? X plus JY. The real part and imaginary parts. In this case, it means no X. X is equal to 0. Y is equal to 1. So you plot that out in your complex plane, it means what? This is your real part X, this is your imaginary part Y. X is equal to 0 and Y is equal to 1. Okay? So it is here. So this standard form. Polar form is actually just to draw a vector from the origin to the point. Then you get a vector. Now this vector has an angle of 90 degrees. Right, with respect to the real axis. So this 90 degrees, the magnitude is equal to 1. The magnitude of the vector is equal to 1. So we put 1 here. 1, 90 degrees. It's in polar form. Now this is actually right, related to your phasor. Your phasor will be analyzed in polar form. Okay, and after that, the only difference now is that for AC analysis, right, this is relating to the gain of the system, because this transfer function, remember, output over input, so it gives you the gain information. This is easier to understand, but how about this one? This is actually a phase difference between your input and output. Remember these transfer functions? So this magnitude is the gain, angle is the phase shift, right, between your input and output at steady state. As I said, we'll go through in more details in AC analysis, right? This is to get you ready for it. So this basically means that the gain times your input magnitude, my input amplitude, times gain give you the output amplitude. So this is my output amplitude, and the phase shift, right, is caused by this angles 90 degree, okay, which means that you introduce a phase shift of 90 degree, but the output amplitude remain the same because the gain is 1. Okay, so let us look at it graphically. If I have an input with a peak-to-peak value of 10, frequency of 2000, then basically my transfer function is 90 degree, right? So I want to predict my output based on my transfer function at this operating frequency. And I know that my gain is 1, right? We have gone through this just now. We know that the gain is 1. So 10, right? Input amplitude 10 times 1 give you the output amplitude is also 10. Now if the gain is 2, then it becomes 20, right? Gain is 10, it becomes 100. So this is the amplitude of your output. Is easier to understand. Okay, the other one is just phase shift. That means that if your input is 200T, then it will be shifted, right, by 90 degree. Then it becomes 200T plus 90 at steady state. Okay, which means that if I have an input, okay, because gain is equal to 1, my output amplitude is 1. This phase angle is 90 degree, so this is shifted by 90 degree. And if you put it in the oscilloscope for two signals, right? Blue one is input, red one is input, blue one is output, you'll see that they will not coincide. There will be a shift, and in this case 90 degree. Now suppose that is other angle, then it just means that the phase shift, right, is different. Okay? And this depends on your frequency, remember. Right? This is at a frequency of 2000. For other frequency, you have different gain, you have different phase shift. Okay? But the output will always be a sine wave. These linear circuits, AC input, AC output. All right? AC input, AC output. The difference is the amplitude, depending on the gain, phase shift, depending on the angles. Right? In this case, 90 degree, what does it mean? One period is 360 degree. 1/4, right? It's shifted by 1/4 of the period. So therefore, it's 90 degree. Okay, that means that we can predict the output at steady state, right? Take note only steady state. Okay, the other input is DC. Remember, there's one more input, 5 volts. Now, actually, DC is a special case where for frequency domain analysis where omega is equal to 0, no frequency, constant. All right. So you put frequency equal to 0, then your transfer function becomes 0. Right? Becomes 0. 0 divided by this is 0, which means that your output will be 0 because your gain is 0. Correct? Gain 0 multiplied by any input, not only 5 volts, any input will always give you 0. Okay, so this is just to let you know that your DC is a special case of AC where omega is equal to 0, right? If you want to see the DC response, put omega equal to 0. Okay, finally, this is just to relate to what you have learned before. Remember your DC analysis, it says that your inductor will behave like a short circuit, right? Inductors will behave like a short circuits in time domain analysis. Short circuits means 0 volts, so it's consistent, okay, which means that because it's short circuits, if 0 impedance, right? 0 impedance, so therefore you always be 0 volt at steady state with a DC input. Right? Take note this for DC. For AC, you can see that there will be some signals. So actually, these capacitors, right, can also be used to block DC signals. Okay, which means that if you have circuits with offset is DC, right? You can use these capacitors to actually decouple, right, to block the DC. So in the end, only AC will pass through. Okay, that's all for the tutorial today. Any questions? Right, for the last part, I go through a bit fast, but don't worry because we will go through that again, right, in the frequency domain analysis. As I said, this is just to get you ready, right, for the frequency domain analysis. Basically, there are some concepts here which I've gone through: gain, phase shift, right, gain and phase shift. And then later on, we use phasor. It's also the same. That means that your phasors input multiplied by transfer functions gives you the output in phasor forms, right? Output in phasor forms, then you convert it back to time domain through that. Okay, if no question, I'll stop here today. Thank you.